Hello everyone, welcome to Computer Science E7. This is lecture 5, optics. So last week we were talking about exposure and metering, how I showed you this very enticing slide, oh there it is, of a gray screen, and basically I said that this is how a camera tries to meter a scene. And last semester, while I was giving that same lecture, a student that happened to be sitting in the class, I'm not sure if he really believed me or if he was just looking for himself, but what he did was he caught a very flattering photo of me trying to decide how to answer a particular question, and using an example that I gave about taking a photo of the projector with me standing right next to it, talking about metering and exposure values. And basically, as you can see, what I was trying to say was that with the very bright projector that's emitting this image onto the screen, if you try to take a photo of that image plus me in it, it's going to be a fairly underexposed image. And the reason for that is because of this gray screen. So the camera is trying to make just sort of this average level of exposure, just this sort of middle gray that exists within it. And that's exactly what happened in this photo. It tries to make everything this sort of middle gray, and so as a result, it might have achieved that, but it looks to us to be fairly underexposed, and it's actually worse on this projector than it is on the screen. And so the camera then, it just tries to make the exposure values so that it looks to be this sort of middle gray. And we talked about these different exposure modes, or these different camera modes that your camera will have to try to help you figure out what exposure values you should use. And so we looked at this camera this photo of a 5D, which has a couple of camera modes where the camera will decide maybe one or two of the exposure values, but you have to do the rest of the work. You have to decide for yourself what the other ones will be. And we talked about shutter speed priority and the perhaps more popular aperture priority, where you can define an f number or an aperture that your camera will use, and possibly also the ISO for your camera, and the camera will determine then the shutter speed for you as well. And as we saw from this previous image, cameras don't always get the exposure right. So we also talked about exposure compensation as a way of telling the camera how to fix the problems of its exposure, how we can adjust the exposure to be as we would expect, a little bit brighter or a little bit darker. So we move on from exposure onto talking about optics and lenses and some of the stuff that happens behind the scenes, so to speak, on your camera. And what's interesting about this stuff is that the technology doesn't really change all that much. So whereas the camera body is very much like a computer these days, where it's every couple of years they're coming out with new ones that are much faster, have many more features, and are always expanding their speed and their number of megapixels and the lineup, basically the feature set lineup that they have. The lenses that you can buy for these cameras don't really change. They do get better over time, but it happens at a much slower pace. So if you're thinking of digital photography as an investment of some kind, or rather the equipment for it, then you shouldn't perhaps be placing so much of an emphasis on the camera body for that reason, because it'll change, the technology will change very quickly, and instead focus your money on lenses, because a lot of the stuff that is out there right now isn't going to change very much in the next few years. So if you are going to, so like I said, if you're going to buy this stuff, then invest in lenses, because this is also one of the things, this is what focuses the light, and the light is what makes the image on your camera. And so if you don't have very good lenses, then you might suffer. Well, it's not to say that inexpensive lenses are necessarily extremely poor. It's just that sometimes that is the case, and sometimes you get what you pay for in terms of these lenses. You can have a little bit more reach, or you can get much larger apertures, so you can get a lot more light into your camera. And it really depends on the goal of your photography and what you're trying to do. And so we have actually already talked about something that's very appropriate and very relevant to the optics lecture today, and that is the f-stop, or the f number, is very much an equation that deals with a number of the factors that go into some of these lenses. So if you remember, what is the F number? Now pretend like I didn't leave the equation up on the board. So it says F divided by D, but what does that mean? Yeah, the focal length divided by basically the diameter of the aperture. And it's not to say that it's the diameter of the lens necessarily, because of the complex ways that the light is being manipulated inside of the lens. It could actually be a little bit less than the diameter itself. Now, one of the things that's important to realize about lenses is that this focal length has, well, obviously a very large impact on how your end results will look. But what some people don't realize is that not all focal lengths are created the same. And in other words, you can buy lenses that have focal length ranges that are completely different than other lenses. And this goes even beyond this concept of, say, 4x optical zoom or 6x optical zoom that these digital camera manufacturers love to put on their compact cameras. Those really go through a range of focal lengths that are somewhat normal, a very normal range of focal lengths. In other words, you could have a very wide shot by zooming out all the way and then get to a reasonably, telescopic or reasonably telephoto view just with that one lens. However, when you get up to the SLR world, lenses don't really work the same way. There are some lenses that do cover that sort of same range, but there are others that are intended for an entirely different purpose. So you might have a zoom lens, for example, that would focus primarily, that would have focal length range primarily in sort of the telephoto region. Or you would have some that are primarily in the wide angle region, and then you would have this sort of gap probably in your equipment of focal length ranges. But also, lenses are available for your digital SLR that don't actually zoom at all, and they're called prime lenses, and I think we referenced them before. And they're much smaller and much lighter than their zoom counterparts because they're not as complex. They don't have to do as much work, so to speak, in terms of focusing the light and doing a very good job of it through this sort of focal length range that exists. And I hope I've already ranted before about my optical versus digital zoom, sort of the problem that I have with that. If you have digital zoom on your camera, disable it. It's completely useless. You're not doing yourself any favors. Just later on, go back and crop the photo if you actually want to do a digital zoom like that. Now, I've been showing this same sort of diagram for a while now about how, oversimplifying a lens and saying, okay, well, there's basically this glass element that focuses the light onto a single point on the film plane. But as we know, lenses are actually quite a bit more complicated than this. And in fact, there's many glass elements within them, and they're shaped differently, they do different things, and we're not going to really go into how to design a lens or what each of these particular elements do, but it is important to realize that these lenses are complex systems, and they're not that easy for us to comment on in a very quantitative way, much less perhaps be able to engineer them ourselves. If any of you are optical engineers, then you should probably be talking about this instead of me, just because it's very interesting, but it's also really, really complex. And to show you, in fact, I do have one of these really neat videos from this show on the Discovery Channel called How It's Made. And if you've ever seen this show, what they do is they have this sort of silly music on in the background with, really canned and sort of funny shots. But what they do show you is how these things and how various things, and in this one particular episode, it is lenses. All right, let's see. It actually shows you how these are made. So here I'm going to show you how these are made.
These television lenses start with a very precise design. A diamond blade slices up a block of specially selected optical glass, while coolant prevents the blade from burning it. The slices then go under a diamond drill, which cuts several puck-sized discs from one glass slice. The operator is careful to keep waste to a minimum. Optical glass costs up to $1,000 per kilogram. During the drilling, the optical glass sits on a thinner piece of glass covered with wax. As the wax is melted, the discs are easily pulled away. Next, a device spins one of the discs while a wheel overhead sculpts it into a lens. The operator checks each lens for chips, and this one looks smooth. This tar-like substance is called pitch. The edges of the lenses have been built up with tape to contain the pitch. They completely coat the underside of the lens with it. Several pitch-covered lenses are now in a metal shell. A worker picks up a hot aluminum dome called a blocking body. He presses it onto the pitch-covered lenses, and the pitch melts onto it. Dousing it with water causes the pitch to harden, sealing the lenses to the blocking body. The blocking body is now upside down and acting as a holding device as it oscillates on a spinning grinding shell. The grinding makes the surface of the lenses uniform and smooth. They place a polisher on the lenses. It's lubricated with a very fine abrasive. For about an hour, the polisher oscillates while the block spins. Polishing makes the lenses smooth and transparent. It also gives them an even more curved profile. The lenses have been removed from the block, and it's time to cut the diameter down to size. Using a microscope, a technician centers a lens between two brass chucks. A diamond blade at the back cuts the lens as the technician monitors it. He's making sure the diameter and axis of the lens have a common center. Next, they group some lenses on round racks called planets. Their universe is a vacuum chamber. The technician closes the door, and the planets continue their orbit. Inside this vacuum, an electron beam evaporates coating materials. The vapor rises to give the lenses a protective coat. A computer monitors the rate of evaporation and the coating. But there's much more to come. Up next, this process really gets visual as all the pieces of the camera lens come together. The lenses have just spent 3 hours getting a protective finish. It's time to wipe away any residue and make sure they're perfect. This particular lens is concave. She covers it to protect it while she cleans and inspects a lens with the opposite profile, convex. Then the convex lens goes to another technician who places it in a holding device. He looks into a microscope and adjusts the position of the lens until it's optically centered. He uses wax to keep the lens from shifting in the holding device. They give the lens another cleaning. Each one must be absolutely spotless before they proceed to the next step. Otherwise, dust particles could become trapped within the optical system and affect image quality. Now that the surface of the convex lens is immaculate, she dabs optical cement onto the center of it. She gives the other concave lens a little more scrutiny before she cements it onto the convex lens. She applies pressure to spread the cement between the two lenses. Cementing them together means they'll be less likely to shift around in the lens barrel. She checks for dust one more time. Then it's under the microscope for an optical alignment of this double lens. Because the cement isn't yet dry, he can push the top lens around and adjust its position. Next, they prep the barrel that will hold the lenses. The technician traces out lettering using a stylus, attached to a sharp tool that engraves information onto the lens barrel. It prints technical details that will tell the photographer just what the lens will do. Things like focal length, the f number, and the size of the aperture opening. These reference points allow the user to pull a picture into focus at the desired magnification. Now they double-check the design for this complex optical system and begin to pull all the pieces together. This singlet, or single lens, goes into the metal barrel first. Other lenses with various curvatures and dimensions follow. She places metal spacers between the lenses to separate them. Proper spacing will prevent aberrations in the image, such as blurring. Between installations, she covers the barrel with a piece of lint-free plastic because eliminating dust continues to be a necessity. One fleck could ruin this entire assembly. Using tweezers, she coaxes the last lens into the barrel. She installs a retaining ring to hold the stack of lenses down. Then she locks it into place. There's one final inspection. She examines the assembled optical lens from all angles. It takes a total of 6 weeks to make one of these optical lenses. And in the end, it's picture perfect.
Now, I don't know about you, but that seems like a really daunting task. I mean, 6 weeks for that. And also, these people at How It's Made, they love their puns. They're always picture perfect. Oh, it's so interesting, but then they have to ruin it with some humor like that. And I'm sure I make my own puns like that you guys grown at. But I mean, really, they should have professional writers or something. It's just me up here. Okay, but anyway, as you can see, these lenses are really complex. It's really quite a thing in order to be able to design and to actually make one. And believe it or not, a great number of lenses are still built by hand even today. So even though that video now looks somewhat dated, it's really not all that old. And especially as you go up the food chain in terms of the lenses, in terms of price, then you get more attention to detail and even a higher amount of expense applied to it. And in fact, I do want to show you this one thing. Let's see, I hope I have it easily available somewhere here. But basically, it's this one prime lens that Canon made for a limited amount of time. And to just give you an idea of a general focal length range. So on a typical SLR camera, you would generally find for a typical zoom lens, maybe somewhere between like, maybe 24 millimeters all the way up to maybe 130 millimeters or so. But Canon made a prime lens that was 1200 millimeters. And this was a very, very large lens. As you get up in size for these lenses, it gets to be really, really, really quite large. And what happened was that they built this lens, and it weighs something like 60 pounds or something crazy like that. And let's see, I have it here. Let's see, I hope I can open this now. But basically, they made it custom order only, so that people with very deep pockets would be able to order one, and then they would build it by hand and they would sell it. And I don't know if I'm going to be able to open it right now, but they stopped selling these temporarily, or they stopped selling them just because there was no longer a market for them. And B&H, the large the photo website, picked a few up on the used market, and they're selling now for, guess how much money? 20,000 more. More. Let's see, it is, I think, $120,000 or $130,000. So you would have to sell your house and then some to be able to afford this lens that you couldn't realistically put on any tripod because it weighs 60 pounds. It has its own custom case. It has its own custom tripod, and it makes the camera look so tiny and ridiculously small next to it that it just completely obliterates all of these other things in terms of scale. Yes. The lens would be used for, well, if you wanted to, I guess, get really high resolution pictures of your neighbors through their window. But more seriously, I think it was used for sporting events, specifically like the Olympic Games, where photographers have to be somewhat far away, especially wildlife photos, where you really have to get a good amount of distance away from the person. And I saw this on B&H and I saved it, and oh wait, maybe I can do it here. Oh yes, here it is. Okay, so this is the lens, and again, it looks small, but this is not a handle for one hand. It is a very large device, and you can see the price over here. Oops, zoom down too much. $120,000. And look at this great deal that you can lease. You can lease it for only $4,000 a month. So if a number of us moved to cheaper apartments, we could put our money together and lease this particular device. Yes?
I was just curious about the video, like how representative, the labor intensity of making that lens, like how representative is that compared to your average SLR lens? I mean, are they all made like that?
So back to the video. So I suspect that most inexpensive lenses are now automated to a certain degree, so that there's less human interaction in terms of their construction. But as far as I know, it's still very much a manual process, especially for some of the moderately priced to some of the more expensive lenses, such as this one. This one was most certainly built by hand by Canon folks, and most likely in Japan in their lens factories there. But I think even Canon, you can find on their website, they were very proud of their own lens creation facility, and they have, I think, some videos of the inside there that's not exactly the same, but they actually have some short videos or even some photos of the insides of it. And it's again, it's basically just a place where people are doing this by hand. They are actually creating these lenses by hand. Yes? Yes, so it's a very good point. So a lens like this would definitely do damage to the body. Now there's a reason that you see on these larger lenses a plate down at the bottom of the lens. Even on this one, there's a plate on the bottom. And the reason for this is exactly for that reason, that once a lens reaches a certain heft, which is about the same weight as the camera, if not more, then you're putting more strain on the mount, on the actual metal part that interfaces between the camera body and the lens. By mounting the camera to a tripod and putting the lens on top of that. So usually you will see a plate like this to mount the tripod to the lens instead, and then you put the lens on the tripod, and then you just attach the camera to the lens, and it just hangs there. And it's unnerving for if the first time you do it, but when you realize that because this now is actually the center of gravity for the whole system, you realize that it's a lot more stable. So even on a lens like this, which is, it is larger, but it's not that heavy really. There's a little place for what's called the tripod collar, this little ring right here. You can purchase it separately and put it on the tripod, and it actually honestly would help even a lens like this, because if it's loose enough, what happens is that the camera has a tendency to fall forward because the weight of the lens will pull it down like that. And so it's easier not only for you but also on the tripod to mount the lens, to mount the camera to the lens rather than the other way around. And so yeah, this camera did have, or this lens rather, I believe came with its own tripod that was capable of supporting the weight, but also you would almost certainly use attach the camera to that lens once you've attached it to the tripod, and not the other way around. Otherwise it would topple over, and there goes your $120,000 investment as it breaks apart into a million pieces. But I think some people that use this lens, I'm not actually 100% sure, but I think they use two tripods, one for for the lens itself, and then if they needed extra stability, they attached it to the tripod and got extra stability that way. Yes.
What's usually the difference between high and low cost lenses? I mean, and like which manufacturer better, Nikon versus Canon, or Carl Zeiss? What is it?
Oh man.
Optical glass that you're using, or
So.
better or higher quality?
So cost, yes. So cost is a very complex question that involves a number of things. So from the slide that is here, let's see, you'll notice that in this diagram, a couple of the lens elements have different colors attributed to them, and I didn't paste a glossary of them here, but and I forget now which lens this is even from. This is, I think, from a relatively small, relatively simple lens. But most camera manufacturers have different types of elements that they can put inside. So they might have optical glass, but this optical glass might have some sort of special coating on it to help try to reduce the amount of color dispersion, for example. And so that might be one type of glass, so this green one, for example. Then there's another one that's called aspherical. So rather than being a lens that's shaped like this, and rather than it being as if it were a sector from a sphere, if you had a sphere and then you cut off a slice and you basically use that as a lens, they have aspherical ones which are sort of flared out on the side a little bit, so they're not as if they were from a perfect sphere. Usually that costs a little bit more money as well, so that might be this yellow color, for example. And so there are these other factors and other pieces of technology within the lens that can contribute to its high cost, including some of these different types of elements like fluorite lenses. Fluorite lens elements, for example, I think are a special type of glass that I'm not too familiar with, other than it has special color dispersion properties, which is supposed to help reduce the amount of color dispersion within it. And so you will typically only find in very expensive glass, and usually only one element of it, because it is that expensive of an element. But even as you get higher up into the lens categories, they often will also have additional electronic components as well. So maybe faster autofocus motors, for example, or the capability to do image stabilization, or some other little doodads and other technical things that can make it a much more expensive thing. And so it's very subjective to say which camera manufacturer has the best lenses between, say, Canon and Nikon. I think the general consensus online from people that talk about lenses and the technical details behind them is that for the longest time, Canon had the upper edge in the longer lenses, so in the very telephoto lenses. And so these white lenses, for example, are actually very popular, especially in the Olympic Games, which, let's see, I hope I have that photo now. I don't have access to it right now, but I think I might have shown you this photo once of basically the sidelines of an Olympic game, and it was basically a whole bunch of photographers, and it was just white lens after white lens after white lens, and for the longest time, those white lenses were attributed to Canon. Like those were the Canon lenses to have, and Nikon right now has sort of the upper edge in wide-angle lenses, and in especially the not the lower end lenses necessarily, but the less expensive glass. Nikon will typically have better quality than the Canon side. So Canon is good if you really want to spend a lot of money on telephoto lenses, but Nikon might be better if you want the best quality wide-angle lens. But really, when you get down to it, it really doesn't matter that much. They're both very, very high quality, and you will get very good lenses even out of both of them. And in fact, you wouldn't know it, but this lens is 16 years old. It was built in 1993. It has an autofocus, and it works just like, I mean, I bought this used, but it works just like the day that it was bought, because it autofocuses quickly, and it has some very, very good optical qualities to it. And so it just brings back this idea that I was talking about before of purchasing high quality glass, and you will be able to use it somewhat as an investment, and you can keep using it throughout time. Yes? Has it devalued significantly? So I didn't buy it that long ago, honestly. And by now, I think lenses only really devalue when newer versions of the same lens comes out. Then the older models get sort of bumped down to a lower tier in cost. So until another lens like this is released, then that'll be sort of the next depreciation hit. But for the most part, lenses that are in good condition and are used, they retain most of their value. There's a little bit of a hit initially. As soon as you buy it, as with most things, there's a little bit of a hit, but then it sort of retains that value as long as you keep it in reasonably good condition throughout the time that you own it, unless for some reason there's something really wrong with it, or something abnormal with that lens or with that particular series of lenses. Okay, but before we go into full-blown Q&A mode, I do actually have a number of things to talk about as it relates to this optic lecture.